So I now just want to know that if this way my screen goes off or not.
No, I think we're on. Yeah.
Can you see the screen
I'll
right now?
start. Yeah, I can. I'll start.
Mm-hmm.
Um, Wait, let me check how many people are here. Okay. Hi everyone. So yeah, I know that a lot of you have been waiting for this Classiq watch party, but I just want to give you a quick disclaimer that this is not going to be like a typical workshop because you guys are students, most of you, and both Arife and I are students as well. So we thought that it might be a good idea to have like a watch party instead of like a full-fledged technical workshop. And I have with me our Turkish ambassador, Arife Ayaz. She's actually Syrian, but she lives in Turkey, and she's a senior in high school. Incredibly talented, you will see going forward. The thing is that we are going to basically take a look at the resources together, particularly the paper that is going to be important for the challenge during the hackathon. And Arife has a good idea of the paper because she has worked with it in the past, so she has a good grasp on the paper. So she might be able to highlight all the important areas that you should look into while you're working on the challenge. As for the challenge, I know that a lot of you are confused, like where do you get the data set? Where do you get the challenge statement details? Where do you submit? And then how do you get judged? I just want to tell you that right before the hackathon, the Ecora platform is going to go live, and that is where you are going to see the entire challenge laid out in like clear details with all the resources, with all the equations, papers, and everything. And you will also submit your projects in the same place in the Cora platform. And right before the hackathon starts, we are going to give you like a quick walkthrough. The Ecora team will give you the walkthrough so that you do not feel lost when you're working there. I'll stop talking and I'll give Arifi the stage. Yeah, go on, Arifi.
All
Start. You
right.
can start.
Thank you,
Yeah.
Nafisa. Now
Mm-hmm.
I will go with the paper. So first of all, let me introduce you about the challenge of Classiq. So in this challenge, the participants must implement a quantum LDE algorithm and then apply it to a quantum harmonic oscillator, which will provide the equation for later on the hackathon kickoff. And then they will compute some energy versus time graphs and study the parameter sensitivity, like the amplitude bounds in state preparation, and they will assess the circuit depth and width under different optimization settings. So here we will first go through the paper, and actually this is a very fundamental paper for the quantum algorithms for linear equations. As you can see, this is the maybe the first paper to implement this idea about truncated Taylor series approximation of the linear equations. So here, let me start. The fundamental equation that this paper deals with is this one, as you can see here. This equation, and actually the analytical solution of this equation is given under this notation here, under here. And in this analytical solution, the problem is that we have an exponential term with the matrix of an n times n matrix, which is hard to compute classically. And with this analytical solution, if we apply this classically, actually this will depend on the matrix, and if the matrix is a high dimension matrix, then this will go exponentially in the complexity. And actually, this paper and the key insight of this paper is surprisingly simple. And instead of computing this term, the e to the power of mt directly, we approximate it with a truncated Taylor expansion. So the entire quantum algorithm reduces to can we implement powers of m efficiently? And the problem is now reduced to applying the identity then m to the power of 1, m to the power of 2, m to the power of 3, and this goes on to the k power with the correct amplitudes. And the algorithm in this paper actually computes this using the Taylor expansion of the e to the power of mt, with controlled applications of the matrix powers and ancilla-based amplitude encoding. And let's go down to the implementation steps. Here we have four implementation steps of this algorithm. Uh, the first one is encoding, then the entanglement creation, and then decoding, and finally the measurement. And let's go step by step with them. We first prepared an ancilla register that encodes the Taylor coefficients. The amplitudes are proportional to a certain term, and so that the order m is stored in a superposition. Here they provide this with the equation, but you don't have to go with the math this much because this needs to be derived with certain equations, which you will see in the appendix section. And with this one, the ancilla doesn't store the solution, but stores the power index of it. And the second step is the control powers, which you can see here with the entanglement creation step. And in this step, we apply control operations, and this creates entanglement between order and the state. And it's the most important conceptual point of this paper, actually. And this is where the Taylor series is built in parallel. And then there comes the decoding state. Uh, we reverse the encoding circuit, and this causes constructive interference in the subspace where the ancillas return to the zero state. And this is the interference trick that happens in this equation, so that when we measure it, we post-select on ancillas being zero, and the work register now contains the solution vector. So let me sum this up. The encoding step prepares a superposition of Taylor orders, and this encodes the coefficients. Then the control powers applies the a to the power of m equation. Then it builds series terms, and then we uncompute or we decode it to clean the ancilla, and then we extract the solution. And finally, the measurement for both selecting and then getting the final state, and which is in the order of encodes, apply powers in superposition, then interfere, and extract solution. And actually, this pattern appears in many quantum linear algebra algorithms if you go deeper in this area. So here, after doing that, actually, we will encounter several cases. The first one is that our matrix that we have discussed is unitary, which is actually rare, and that means we can directly encode the control powers of the matrix. But our real-world matrix is usually non-unitary. So they introduce in this paper this linear combination of unitaries, this equation here that you can see, and we decompose the matrix into a linear combination of unitary matrices, and this introduces another ancilla register. And actually here, why the circuit grows. So here we have more registers, more controls, and then more depth. And actually, there are some technical details like the count of ancilla qubits here, and then how the error bound is calculated, and the query complexity, which you can see here, is related to the K, which is our accuracy metric. And the accuracy improves as we increase this K. But if K increases, the circuit depth, the number of ancillas, and the query complexity is also going to increase, and here we have to optimize to choose the K carefully. And the algorithm assumes we can efficiently prepare the state, but this is not trivial. If state preparation costs the complexity of O(n), then we lose the exponential speed up. And this assumption is standard in many quantum linear algebra algorithms, but it's also one of the biggest practical challenges of it. So the conclusion of all this is that the quantum advantage depends heavily on the input model. So here we have to decide how to encode it and how to decide on the input model and what algorithm to use to not lose that exponential speed up. And actually, in the paper itself, they have implemented here in the results, they have implemented this approach on a 4-qubit NMR processor. And the fidelity they have acquired was 93%. And this demonstrates that the abstract algorithm can be mapped to real hardware. And with the scale, if we are trying to increase the accuracy, we just have to account for the hardware constraints of the circuit depth and the number of ancillas we will acquire. And this is exactly what you will explore in the hackathon. So the exact statement is that how parameter choices affect energy accuracy and resource cost in this challenge. So you will explore how parameter choices affect energy accuracy, and this is directly about the Taylor order K, the amplitude bounds, and the state preparation precision. And to sum it up, larger K, more accuracy, but larger K also means deeper circuits. And non-unitary matrices means more ancillas, and with linear combination of unitaries, this will cause more controlled operations. So here you will have to optimize. And before we continue with the Classiq platform, it's important to note that the algorithm in this paper is not the only quantum approach to solve linear differential equations. And in principle, we could also solve the problem using the HHL algorithm by reformulating the time evolution as a large linear system. We may use the Hamiltonian simulation, or alternatively, if the generator is Hermitian or can be embedded into Hermitian matrix, we can use the Hamiltonian simulation, as I said, to the exponential. And more modern approaches are actually like the quantum singular value transformation can be implemented, can implement matrix functions like the exponential in an early optimal way using the polynomial transformations. And actually, each approach has its different dependencies on condition number, sparsity, or the state preparation. So in this paper, we focus on the Taylor approach because it is conceptually transparent and easier to implement with our constraints. And the real question among these algorithms is that under what assumptions do they give an advantage, and what are the resource trade-offs of them? So I will be sharing these papers with you about the HHL and the QSPT and the Hamiltonian simulations, so you can explore this further if you don't want to go with the Taylor approximation idea here proposed in this paper. And if you want to explore this paper further, you can go to the appendix and then explore how they have derived the mathematical model of this one. And let me now stop this sharing and share with you the Classiq website. So here you can see in the GitHub.
Arife, before you do that, we have a question. And the question says that what math should we scheme and what math wish should we focus on understanding? Like which equation would you like highlight in the paper?
Hmm. I will actually, in this paper, they are using an arbitrary state of this equation. So in our challenge statement, we will not use the same equation, but if you want to understand the logic of how they are solving the matrix, then you have to understand how they are deriving the analytical solution. And actually, I can provide that because I have worked on this before. And actually, the important part is how they are deriving the analytical solution and how that solution is mapped to the Taylor approximation. And the other math is actually not that important because here they are deriving this particular math for that particular equation, not for the one that we will be providing for the challenge. And I hope
Awesome.
that was
Yeah.
informative.
You
Yeah.
answered it nicely.
So
Yeah,
so
I
now,
guess before we move on to the Classiq platform, another concern that I've been seeing on Discord is some people are having trouble logging into the platform and all. I just wanted to tell you that we are going to have dedicated channels for each of the challenges, and these will unlock right when the hackathon starts. So you will get the particular role based on the track that you have selected. For example, if you have selected track C, then you'll get the role track C Classiq, and then you'll get redirected to that channel, and you can ask all kinds of technical questions there. But actually, the better option is to just go to the Classiq Slack channel, and we have given you the link in the preparation materials GitHub repository. So you can just join their Slack channel, and they're going to be the Classiq team is going to be there to answer your questions in real time. So I guess that's a better, a better option, like getting answers really fast from the Classiq team itself. Yeah, I guess that's it. Arife, go on.
okay, then I will go on. Here, for the challenge, we will be using the Classiq platform and the SDK of the Classiq, and actually the output will be a Jupyter notebook. So I will show you how to go with the environment and how to create that notebook. And before going to that, I will just show you here and take your notation about the preparation materials, and that you can go here with the Classiq 101. The Classiq library is actually present in the environment, so you don't have to go to it in a different website. And as Nafisa has said, you can ask the Classiq community Slack. You can have your questions there, and if you have any technical questions regarding the SDK, you can ask it in the channel as well. So I will now go with the platform. This is the link of the platform. We will share it with you in the Discord later. And after you sign in, it's actually pretty easy to sign in. You will not have any credentials or anything. You will just hop into this page, and then after signing in, you will find that in this section you will have several options, which are one of them is modeling, which you can use for the algorithms and transparently synthesizing them. So here you can just put synthesizing, and you can use here the ready to use algorithms. This in the quantum program, it will just prepare the state and then show you how this is demonstrated. You can go to the execution and then see what happened and the jobs for the results. But mainly for the hackathon, you will use the environment itself that is ready to use here. And here is the environment. You can see here that the Classiq library is present. So you can go here and explore the algorithms further. If you don't want to go through the preparation materials in here, you can actually use them directly in the environment. You can go here and just have a look on the algorithms and how the documentation is going on, and maybe basic tutorials to see the differential equations as they have some. Uh, Here you can see it, the quantum differential equation solvers. And for your workspace, you will be working in the user workspace under this one. And you can actually just create the test IPYMB. Here you will have a notebook. So I have just created another one. So here you can see that the environment is actually ready. So you just have to import the Classiq, and the Classiq is actually in the environment itself, so you don't have to pip anything. And this is how it works. And you will be working with this one, so you don't have any compatibility issues with the documentation and the Classiq library. And I think this is all I can share about the environment and the Classiq platform. If you want to utilize these execution models, you can use them for visualization. But mainly, I think I would suggest that you just stay in this environment and then work on this. Uh, And after that, we have gone through this. I will just show you what Classiq 101 is having. And actually, these tutorials are pretty helpful with the SDK. So you can go through them if you are in the Classiq track. And you can get familiar with the documentation and the SDK before the hackathon. And yeah, that is all we have for the Classiq. If you have any questions, we will be present in the Discord, and the Classiq team will be present on the Slack community. So this is the end of this walkthrough. Thank you all for listening.
Thank you, Arife. That was wonderful. I wish we could actually like get the live stream on our YouTube channel right away, but it will take some time to process the video and then get it on our YouTube channel so that others can see. But I'm really hoping that since everyone has a link to the live stream, they can come here at any time and they will be able to watch the whole, walkthrough. I think it's really important because some people are really having issues with the platform as well as how to like approach the paper and all that. So yeah, thank you once again. And again, if you guys have questions, we are on Discord, and I think the better solution is you join the Classiq Slack channel as soon as possible, because the Classiq team is going to be there to answer your questions. Okay, I guess we can wrap up now. Uh, oh, another thing. We were also supposed to have a watch party for the Rigetti track. I don't know why I'm saying that in the Classiq resource watch party, but I should still mention it. We're going to have something similar, but it's going to take a little more time. So I think it's best to just kind of push it a little bit back, but we're going to have it right before the hackathon. So yeah, and you will be able to watch both of the sessions during the hackathon. So no worries there. All right, that's all I had to say. Thank you again. Bye bye, Arife.
Bye bye.